Let's have a look at a more sophisticated adaptive control method, somewhat more recent method for doing improving our accuracy and getting an estimate of what the error is. The method is called the Bullirsch Stoer method. So imagine that we're trying to integrate from a point x to some point x plus capital H. And what we're doing here is we're choosing a macro step, h, which is very much bigger than your typical step size h. So for example, if we were integrating from x is equal to 0 to 100, then you might choose h to be 10. And it will be comprised of integrating from x to x plus big H will be comprised of a series of smaller steps h. So the way the Bullirsch Stoer method works is to step from x to x plus h using our ODE integrator, using a small even number of steps. So for example, we might take 2 steps. Start off here, integrate to this point here, and come up here, and the solution we get here we're going to call y2. The 2 refers to the fact that we've taken 2 steps. Then let's do the same thing now. Go back to the beginning at x and integrate using 4 steps forward until we get a solution y4. So we now have 2 estimates of what the solution is at x plus big H. Use these 2 estimates to extrapolate a solution to 0 step size. So y2 and y4 are functions of the step size, so that's going to be big H on 2, big H on 4. Let's extrapolate to n is equal to 0. N is equal to infinity, sorry. In other words, the step size h is equal to 0. If we do that extrapolation, we'll come up with an estimate. We'll call it y infinity, and it's that red blob there. And we'll say that is going to give us an estimate of the error, the difference between y infinity, which is our extrapolated value, and y4. If this error is small enough, our macro step is finished and we can move on to the next one. In other words, go from x plus h to x plus 2h. Else, we go back to the beginning again and use a larger n, in other words, a smaller step size. So for example, n is equal to 6. Our step size now is big H on 6. And we'll come up with another estimate, y6. Now what we do is we use y2, y4 and y6 to extrapolate again to 0 step size, h is equal to 0, or n is equal to infinity. And we'll come up with an estimate. Now, because we're using 3 values of y, we're going to be fitting some quadratic polynomial, and we might expect to get a better answer than the case where we are just using 2 estimates, which is only going to give us a linear polynomial. That's our error. If it's small enough, the macro step is finished, and on we go using more and more points. Once we've got to the point where we have completed our macro step, in other words, our estimate of the error here is small enough, we take this value here, which is our extrapolated value to an infinite number of steps, and we do the process again for another macro step. So now we're going from x plus h to x plus 2h. And eventually on we go. So that's a concept behind the Bullirsch Stoer method. Of course, there's a whole bunch of other things that one needs to take into consideration. So the first of these is that we only want to test a limited range of n values. We don't want to do everything. So for example, we might start with 2, then go to 4, 6, 8, 12, etc. If our solution hasn't converged, in other words, if the error is still too big when we're getting up to quite a high value of n, for example, n is equal to 96, then it's likely that the function is behaving badly over our macro step. So we need to reduce that. So for example, if we had a solution that looked like this, and we were trying to integrate from this point here to this point here using one single big H, we do fine at these points on the side, but as soon as we got to this bit in the middle, the function's obviously behaving very rapidly, changing very rapidly, and we need to integrate more carefully in that region. So what that suggests is we need to take a smaller value of big H. Related to this, of course, then, is that both for efficiency and accuracy, we either want to increase or decrease it to keep the errors under control, but also, ideally, we want to keep the maximum n that gives us an acceptable error around about the same. So we don't want it to be 100 in one interval, and 500 in the next interval. We also want to limit the number of values we use in the extrapolation. So, for example, once we got into 48 points, the estimate that we had all the way back when we only had 2 points adds little relevant information to the extrapolation, and indeed may cause us problems due to things like wiggles. The recommendation is to use at most 6 or 7 recent guesses. That's the Bullirsch Stoer method, and that's it for adaptive step size control. So just to summarize that topic, Richardson extrapolation works for ordinary differential equations. If you know the order of the method, then we need to use 2 different step sizes to remove the leading order error term. That's essential, however. You have to know what that error is, or how it scales. Use of 2 different step sizes also allows you to make an estimate of the error. We've been through that in a couple of these videos, but ensure you know how to do this, because this is potentially examinable. The error estimate can be used to choose an appropriate step size then, and that's what we looked at in the adaptive RK4 method. Remember, we want the step size to be as big as possible for reasons of efficiency, but small enough to ensure that a specified error tolerance is met. And there's a couple of reading resources here on adaptive step size control if you want to do a little bit more.